Welcome. This Unity Pro Experts video provides an overview of a solution for communicating to field devices equipped with Modbus serial interfaces and turning the device's raw data into usable information. There will also be a few tips and tricks shared. Within a Schneider Electric plant structure architecture, these field devices are found down here in the field. Schneider Electric has hundreds of devices available with Modbus interfaces, and many other manufacturers do as well. I will not even guess how many of these devices are in service in systems today, but it is certainly a very big number. The solution being demonstrated uses the Schneider Electric TSST Motor Management Controller as the field device. The serial Modbus network is RS-485 2-wire, which is typical and commonly used today. A Schneider Electric plant structure architecture is based on Ethernet, so this solution includes a Connexium ETG100 gateway to convert Modbus Ethernet to Modbus serial. This solution is not limited to TSST and is easily adaptable to many different device types, and there are no issues mixing the types of field devices, providing they all have common port parameters like baud rate, parity, etc. Any Modicon Unity process automation controller can be used, and communications can be from any local Ethernet port of the system. These include Quantum, Premium, M340, M580, and Momentum. The solution is Unity Pro DFBs, and there is a DFB instance for each device in the solution. Here is a general overview of the solution. There is a DFB, the ETG100 polar, that manages the device polling sequence, and a DFB of type TSST 2-wire ETG for each TSST field device. How does this work? Well, the polar DFB and the device DFBs share a data structure. In this structure, the polar assigns the Modbus address of the device to poll into an integer element of the structure. When each of the device DFBs is scanned, if the device's Modbus address matches, then the device DFB communicates to the TSST. When the communications are done, the device DFB reports this back through the shared data structure, and the polar moves on to the next device to be polled. It does its stuff, reports back, and this cycle simply continues on and on and on. Pretty simple so far, huh? Okay, so here is the polar DFB. It manages the polling sequence for up to 32 devices. The shared data structure or interface is shown. The poll address is where the Modbus address of the device to poll is stored, and the device done is where the device DFB will write its Modbus address into when its polling is complete. The write queue is a FIFO, and if any device DFB has state changes on data that needs to be written to the device, then that device DFB puts its Modbus address into the write queue. Here is an illustration of the polling sequence. If the poller has given the baton to device 2 with Modbus address 3, and device 5 detects that a write command is required, then the device 5 DFB puts its Modbus address 23 into the write queue at the first unoccupied location. When polling of device 2 is complete, the poller passes the baton to device 5 and it executes its write command followed by a read status command. When done, the poller returns to normal polling sequence at device 3 with Modbus address 2. Here are the public variables for the poller. These include a table for the 32 devices that can be polled, and the user can assign the Modbus address for each device. I am not going to review the polar DFB code, but I will point out some tips and tricks used. First tip, know that you can directly reference system words and bits inside of a DFB, like this one, which is the first scan bit. And here is a trick. You can use structured text statements on the input pins of elementary functions, elementary function blocks, and derived function blocks to clean up or compact function block diagram logic. Here is an example of what this accomplishes. During development of this DFB, you can see what the code looked like, and then after debugging, I compacted it so it is physically smaller in the function block diagram editor. This trick was used in many places within the DFBs for this solution. Here is another tip. Reduce typing, and you know I'm all about that, by referencing elementary function block and/or derived function block output pins. This eliminates unnecessary variables, and that keeps my hands off the keyboard. Now let's look at the TSST DFB. There are 3 example DFBs provided. Each is optimized for ease of use via the U2V DFB Manager, communications efficiency, and scan time impact. Descriptions of the 3 provided examples show the controller supported and other details are provided. Pause here to review. These DFBs are designed for a TSST configured for independent operating mode and using 2-wire local control with network control selectable and with an LTME expansion module. These DFBs can also be easily adapted for other TSST configurations. These DFBs execute the polling of the TSST by reading the status registers every poll, reading data registers like voltage and current using a staggered polling routine. They monitor the command inputs for changes, and on changes poke the device address into the poller's write queue, and they write the command register on demand. This DFB also calculates motor runtime, provides alarms, parses out and conditions the status and data values, and puts these into the data object, output variable of the DFB. Here are the public variables of the DFB for use with quantum and momentum. Pause here to review these. Here is another illustration of the polling sequence, this time from the device DFB's perspective. This is what happens when polling is initiated. Because there are 3 devices, the first 2 polling cycles only include status polling. Beginning on the 3rd polling cycle, the staggering of data polling begins. And during each subsequent poll cycle, one DFB will read both status and data from the TSST. On-demand writing of commands has no impact on the staggered data polling sequence, and if the controller is stopped, the staggered polling sequence is initialized. Here is the data object containing the parsed and conditioned data from the TSST. This is just a partial list. The status and data registers read are shown here. Pause here to review this. The code inside the TSST DFB is modular, making it easily adaptable to other types of devices, like motor-operated valves, flow computers, etc. I will not be getting inside of this DFB. I leave that to you. The example DFBs in this solution are downloadable from the unitypro.experts website. I also recommend that you download the DFB Manager tool. That is a wrap for this solution overview. I hope you will find that this is not just another option for communicating with Modbus serial devices, but one that may solve some problems. Thank you for your time and have a great day. Subscribe to this channel to see more demonstrations of Unity Pro tools, tips, and tricks.